This conference will now be recorded.
Well, welcome everyone to our April webinar, GSA webinar. I want to give a special thanks to RS&H and Rick Rogers as our title sponsor. Also want to just take a moment too to welcome two new members to GSA. First is Carly Scott from Equatorial Launch, Australia, and also Jeremy Ketley and Paul Cremens from the UK Department of Transport. So welcome to you both to the group. Before I go over the agenda real quick, I just want to mention to everyone that in the center top of your screen, you'll see a view everyone drop down. When you go there, you should select active camera option. That will be your best bet for the session. Okay, let me just take a moment to quickly go over the agenda. We've got a pretty full set of items today. We're going to start off with some really exciting stuff from Robert Alon at Leviathan, talking about some activities between Houston, Scotland, and Ecuador. Then Chaz Miller is going to update us on some equally exciting things happening with his working group. So looking forward to that. Then George is going to give a quick update on things from his perspective and introduce our keynote speaker, John Olds. So without further ado, I'd like to turn it over to Robert, and the floor is yours.
Thank you very much. Hello, everybody. We're very excited about this project. This was thought out by David Alexander from the Wright Space Institute, and it has been a wonderful collaboration where we have been able to get schools from Scotland, Houston, and Guayaquil, Ecuador to participate in a downlink with the International Space Station, where we'll have two astronauts live talking to us, and these will also be transmitted through NASA TV. And we have 3 astronauts on the ground also, former astronauts, who are also going to be answering other questions from the students. And this turned out to be a great event where we were able to organize an introductory event and then the main downlink. And in the introductory event, we were able to have the mayor of Houston, Sylvester Turner, and also the Prime Minister of Scotland, former President of Ecuador, Rosalía Arteaga, and the Ecuadorian ambassador in Washington, D.C., and other personalities from the different communities. So it's really exciting how people have decided to come forward in this time of COVID and support this initiative so the communities can be closer together, be able to have those children who have suffered a lot throughout this year during lockdown to be able to interact with one another. So it really opens up the opportunities for closer collaboration between the communities, research programs with the teachers, and hopefully we can think in a post-COVID world about exchange students and visiting the other parts of the world. So I think it's a great opportunity about what spaceport's role can play within the local communities. And my thought, at least, is that everybody in the community should know about their spaceport. That it should be that exciting, that place where everybody wants to go and be and know about. And I think this really allows students to know more about space and what we can go ahead and help the local community. Thank you, James, for the time to share the event. The event is open to the public, so all of you, please feel free to join. I'll put up a link in the chat so you can share it with your friends and family. It's going to be really great to see all these kids interact. Thank you.
Hey, Robert, before I turn it over to Chaz, when the event is tomorrow, isn't it?
That's correct. It's going to be tomorrow from 8 a.m. Until 10 a.m. Central Standard Time.
Okay.
And I'll put the registration link and share it with your friends and family. It should be great.
Okay, cool. Well, thank you, Robert. Now to move a little further north, we'll go to Spaceport America. and hear from Chaz on an update on what's been going on in his working group. Chaz, over to you.
Okay, hi, thanks. Thanks, James. So yeah, quickly to go over this, I've been chairing the Academic Partnerships Working Group. I think we started our first meeting last April, so we've been going for about a year and doing about monthly or meetings or even every 3 weeks. We have, I think half the working group is right here today or more. Karen and Sherry and Robert are here and me, and there's 2 others from Cornwall and from Japan, Shin Takata and Dave Pollard. So we, over the year, sort of struggled around, thought of ideas, went some back alleys and came up with a list of items that we wanted to tackle this year, somewhat ambitious. But the very first one is to represent and guide a local school group for some ISS related projects. We want to get a local group, either through museums or for schools at each of our locations, to be doing an event simultaneously with an organization that does work with the International Space Station. So, and we represent the US and Ecuador and Japan and the UK. So it's kind of interesting with just 6 people, we've got 4 countries represented right there. So we've searched around, we've had a lot of guest speakers to give us ideas of what to do. What we seem to be settling on is a group called Orion's Quest, which is a nonprofit 501c3, which facilitates, creates 1 to 2 week curriculums that actually gets data from the space station that PIs are working with into student classrooms. And that ranges from the middle school to the high school level, what they do. So we're right now in the process. Dan Lowen is one of the project coordinators from that organization. He's been at a couple of our meetings. We're now working on which project we want to do. There's a couple of projects they're working on developing a curriculum for the fall semester this year, and then a few that are a little bit further out into the winter. So once we decide what project we're doing, we're also now connecting with each of our local schools to do that. So we can do that curriculum through Orion's Quest, and then we hope to add some content that we can facilitate and talk about our spaceports that are local, and then even maybe get group connection between all these countries, between the classrooms that we've got. So that's where we're at right now.
Thank you, Chaz. Does anyone have any quick questions they'd like to throw at Chaz or Robert before we move forward? Anything that anyone wants to jump out at? Not for now. Okay, well, feel free.
Sorry, James Outskirters. Yeah, is this a good time to give a quick briefing on the working group, point-to-point working group, or there's a window for that in a bit?
Well, maybe if it's okay with you, Oscar, maybe we could do that after we have the presentation from John.
Fantastic.
If
Fantastic.
That's okay with you. I don't want to shortchange John at this point in any way. So
absolutely. Just let me know. Thank you.
Okay, no, that's cool. Okay, well, moving along here. Next up, George, our chair, and George has a few words to introduce our keynote. So, George, over to you.
Thank you, James. Just to briefly review some of the things that have been going on for those who might have missed some of the items of interest. Of course, we've got a nominee now for the NASA administrator. Former Senator Bill Nelson has been identified by the White House, and understand the confirmation hearings should start as early as Friday of this week, and I think that should go pretty smoothly. NASA also announced Robin Gatens as the new director of the International Space Station program at NASA headquarters. So I've worked with her in the past, and I think she'll be a good partner for us and others. A couple of other personnel items of particular interest to this group. We have a formal appointee for the New Mexico Spaceport executive director, and so I want to congratulate Scott McLaughlin for being formally named to that position. Congratulations, Scott. And
Thank you very much.
Also, Todd Lindner, who has been serving as the director of Cecil Spaceport, was recently hired as the new CEO of the Mojave Air and Spaceport in California. So great new opportunity for Todd, and congratulations to him as well. NASA continues to move forward on preparing the Space Launch System with the completion of the Green Run static fire test at Stennis Space Center on March the 18th. And after the completion of all their data analysis there, we'll be shipping the core stage to the Kennedy Space Center in Florida in preparation for the first launch of the SLS, potentially at the end of this year. On the regulatory front, March 21st was the effective date for the FAA's new streamlined launch and reentry license requirements final rule, which is a big project that has been worked on for the last several years. And so that marks an important milestone. And then many of you may have heard that there's been a lot of discussion about whether the Biden administration would continue the National Space Council. And the White House has announced that, yes, the council will be continued, but we don't have the details yet on exactly what the membership would be and who would chair the group. But we'll be watching that very closely. I think most of the industry was pleased to hear that news. Right at the end of March, we heard from Virgin Galactic that they had rolled out their new vehicle, which they've called the VSS Imagine, for their suborbital space tourism activities, and that'll begin ground testing right away with flight tests expected later on this summer. And they've improved that model in terms of a stronger and lighter structure and systems that will hopefully make it easier to inspect and maintain. So a lot of progress happening there. One final comment on space tourism related items. We're seeing some serious progress and activity now on orbital private space missions. At the end of January, Axim had announced that they've partnered with SpaceX to fly a crew to the space station, consisting of private astronauts, with former NASA astronaut Michael Lopez Alegria as the commander of that mission. And that crew includes folks from the US and from Canada and from Israel. And then just in February, SpaceX announced this new mission called Inspiration 4. You might have heard about that if you watched the Super Bowl and saw one of the commercials on that. And that group includes the commander who bought the flight, Jared Isaacman, from Shift 4 Payments. And he's turning that into a fundraiser for the St. Jude Children's Research Hospital, pledging to raise up to $200 million. And he recently named the other 3 members of his crew, including Haley Arsenault, who's a childhood cancer survivor, and she's now a physician assistant at St. Jude's Children's Research Hospital. And since she's only 29 years old, that would make her the youngest American to travel to space. Right now, they're planning to launch as soon as this September. So we're really starting to see some serious commercial space activities. One of the other topics, of course, that is very much of interest to GSA is the topic of our meeting today, namely point-to-point transportation. And certainly, in my opinion, the ability to conduct extremely high-speed, long-distance transportation, including things like point-to-point transportation through space, is going to be a major game changer for the global economy. And once we have the ability to fly from one side of the earth to the other in only a couple of hours, it's going to really change not only how we travel, but also how we communicate and how we do business. And a lot of people are thinking about that now. It's not clear yet whether that's going to end up being a supersonic or hypersonic flight through the atmosphere or suborbital flights through space. But in either case, the success of the systems will ultimately depend not only on the technology, but also on economic viability. So NASA recently commissioned a market and business analysis of that topic by an independent study team that included SpaceWorks Enterprises Incorporated, Deloitte, and the National Institute of Aerospace. And the study considered key city pairs, market elasticity, ticket prices, vehicle sizes, flight speeds, and vehicle range in some of the models out there. And we are really privileged to have as our keynote speaker today, Dr. John R. Olds, who is the founder of SpaceWorks Enterprises and serves as the company's chairman and CEO. And he has authored or co-authored more than 100 technical papers over the years on advanced space systems. He co-founded the Fast Forward Project Working Group back in 2008 as a collaboration forum for hypersonic commercial flight, and served as the group's executive director through 2013. And Dr. Olds holds a BS in aerospace engineering from NC State University, a master's from Stanford in aeronautics and astronautics, and a PhD in aerospace engineering from NC State University. He's also a professional engineer registered in the state of Georgia and an associate fellow of the AIAA. So, John, over to you. Thanks so much for speaking to us today.
Okay, very good. Greetings, everyone from Atlanta. Hopefully you can hear me. And I'm going to try to share my screen here. I'm going to send that request.
You should have that now, John.
Okay, stand by. Let's see, did you, Steve, did you send me that request?
Yes, you are a presenter now. You should be. Let me see here.
Try one more time.
So do you see the circle at the bottom of the screen called screen? Is that grayed out or is that active?
It's,
Move your cursor on the screen.
there you go. Give me just 1 second. Sorry, everyone.
Do you see the screen sharing icon at the bottom, John?
I do, yeah, but it is grayed out.
All right. What I'm going to do is, hold on.
Yeah, we have to maybe.
Don't do anything right now.
Okay.
We'll get you set up. Are you seeing anything? Can you click on the that screen button?
There you go.
There you go. Oh, looks like you had it.
And John, you're muted now. Okay, we can see your screen now.
Okay. All right, so you can see the screen, and you can hear me okay as well?
Yes.
Okay, now on mine, I'm looking at a preview of my entire screen. Is that what you all see as well?
Yes.
So let me just try this. And does that fill the screen for everyone?
Yes.
Okay, all right. Well, my apologies for that logistical issue, and that's a bit on me. I had a meeting before this one started, and so I was unable to test all of that, so my apologies. But it's good to see everyone, and I hope everyone is doing as well as you can be in this age of COVID. We're struggling along fine, but we're looking forward to the light at the end of the tunnel on our side. George reached out to me, and as he said in the introduction, he would like me to speak a little bit on the recent 6-month study that my company completed along with our team lead, Deloitte, and partner at NIA. There was a parallel team as well. I won't address their findings today, but there was a second team that worked on this in parallel that was led by SAIC and had participants from Bryce and our friend Oscar Garcia at Interflight Global. And so I'm going to present one of 2 of those teams and give you a little bit of an insight into what we learned. But as I begin here, I'm going to introduce you, if you'll bear with me, a little bit to our company. I do know some of you, and it's good to see you all again, but many of you may not be familiar with what SpaceWorks is. We have been around for 21 years in Atlanta, Georgia. We're a small business of about 60 people. We have a couple of locations in Atlanta. One is more office park oriented, and that's where I'm talking to you from today. The other is our production facility, which is around in Doraville on the northeast side of Atlanta. So we have both advanced concepts work and engineering services work. Some of you might be familiar with our market research studies, et cetera. And then we also have some hardware production capability within our company. Let me start here kind of at the beginning, and I apologize to those of you who know these things by heart, but I want to make sure that we're all on the same page with some terminology that I'm going to be using throughout the presentation. And so it's a bit remedial, but let's make sure that we're all talking about the same things. Throughout today, I'm going to talk about aircraft that are capable of traveling at different maximum speeds. Supersonic is a general term to define greater than Mach 1 flight, where Mach 1 is defined as the speed of sound at any particular altitude. And so that's open-ended. Mach 1, greater than Mach 1, all of that is supersonic. And at that point, we get some compressibility in the air that causes shock waves. In common language or references, we often refer to a second dividing point at hypersonic speeds. And that is much more arbitrary, and it's traditionally defined at Mach numbers greater than Mach 5. But I want you all to understand that there's really no magic that happens in fluid flow at Mach 4.99999 and or at Mach 5. It's a bit of an artificial definition that says hypersonic flow regimes tend to look a little different in character. They have very little shock layers, and they're characterized by a lot of heating, a little bit simpler definitions of surface pressures. So when I use the word hypersonic, I typically do mean that to refer to aircraft that can fly greater than Mach 5. But be aware that there's nothing really magic that happens there. And in the study that we considered, we were asked to look at from Mach 2 to Mach 7. So a box from Mach 2 to Mach 7. And that's all of that is supersonic. Some of it is also hypersonic. Flight modes, we talked about today earlier, the idea of ballistic or exo-atmospheric flight that would launch like a rocket vertically and then land either horizontally or vertically at the other location. And then there's the concept of lifting flight. And the study that my team, and actually both teams, considered primarily looked at lifting flight. So the types of results you're going to see from us today are airplane-like things that take off horizontally and things that land horizontally and spend most of their time operating in a lift-producing flight mode. So like SpaceX Starship, that's getting a lot of press lately, and a lot of the work they're doing down in Texas, that was ground ruled out of the study that we're considering. So that wasn't one of the ones we considered. Propulsion class, I think everyone's familiar with a rocket. A rocket carries on board both fuel and oxidizer. Could be a solid, could be a liquid, could be a hybrid, but rockets carry their own fuel and oxidizer on board. Air breathers are what we typically know about how airplanes operate: turbojet, turbofan propulsion. Ramjet, scramjet are those that don't typically use compressible mechanisms like like compressors. They use ram compression. You're familiar with ramjets and scramjets. And then the idea of a dual mode ramjet is one that could both be a ramjet and a scramjet. Scramjet is really a contraction of two words, supersonic combustion, or three words, supersonic combustion ramjet. It's a variation of a ramjet. And then the third area is combined cycle. You might have heard that term before, but combined cycle takes elements of different types of propulsion and makes them into a single integrated propulsion system. And so you've heard of rocket-based combined cycle or turbine-based combined cycle. Those are hybrid type propulsion systems that use a little bit of one or another propulsion class. You'll see that I'm going to be a fan mostly throughout today of either turbojets or turboramjets, but we also have a over-under turbine-based combined cycle concept that I'll show you. And then finally, sales and markets. As I go through the presentation today, we have assumed multiple markets and they're complementary but distinct. Sales to the military for military sales, or to the Department of Defense, Department of State, U.S. government in general, are one type of sales model. Sales to commercial airline operators, think of this as being Boeing's model for supporting American Airlines or Delta. That's a sales model, and we've considered that one. Corporate charter fractional ownership sales, like a NetJet sales or a commercial business jet sales, is another type of market. We typically think of that as being sort of a Gulfstream type of model. We've captured that. And then finally, private owners or single high net worth individual sales. So as we have done an analysis of the future market for high-speed point-to-point transportation, we've considered different buyers at different levels. Some of them could be operators and they buy aircraft. Some of them could be airframers and they buy engines. And then there's the engine developer himself. So those are some basic terminology, and I'll use those terms, but please stop me if there's anything that's not clear. I have a little bit of a commercial still, which is what qualifies my company or me specifically to talk with any kind of authority related to point-to-point transportation. This is a little bit of our resume over the last 20 years, the kinds of things that we've worked on. Prior to joining or founding SpaceWorks, I also was a professor at Georgia Tech, and prior to that, I was a professor at North Carolina State. So some of my background is academic, and then some of it is commercial and private industry. And you might recognize various programs that either NASA or the Air Force has sponsored, and we've been a participant in a number of those over the last 20 years, including the one I'm going to talk about today. George mentioned, and Oscar is on this call today, that my company and I was a co-founder of the Fast Forward project back in 2008. I'll talk a little bit about our work, relevant work at Generation Orbit on a slide or two. And then we also have a number of software development activities that we produce and sell to a number of you out in the industry. So we have a pretty extensive resume in doing this type of work. Okay, high-speed systems, whether they be supersonic or hypersonic, tend to take on different characteristics. Those that fly high tend to be slender vehicles with propulsion systems that can propel them above Mach 3 in many cases. Turbo machinery, turbojets typically tap out at about Mach 3 or so. And so beyond that, you would need some other kind of propulsion system. And so this is an example slide showing you the kinds of things that we at SpaceWorks have developed for a variety of internal and external customers over the years that have to do with high-speed flight systems. And I can talk at length about any of them, but you can see a variety that we've done, including some that may be familiar to you. We did some early work with Virgin Galactic, for example. In the lower part of this slide, we've done work with Leidos on the top left of this slide, and a number of military applications. So these are the kinds of things we've produced. I do specifically want to at least address, some of you are familiar with our work through Generation Orbit on the X-60 project. So we too have an interest in developing hardware that can address the test needs from various CONUS-based or international test sites. Our partnership is with Cecil Spaceport currently, and we're looking at new partnerships with Mojave for some of the hypersonic test applications that Generation Orbit does, and Generation Orbit is a part of our team. So this is some recent accomplishments that I'm showing you on this slide. Fast forward, I know that the Global Spaceport Alliance has a partnership. I've been on some of the working meetings where the two organizations work together. I'm glad to see that collaboration. I think there are a lot of synergies between what the development community is doing in high-speed flight, hypersonic flight even, and what the spaceport community is also doing to develop US-based spaceports as well as international. So I'm glad to see those collaborations. This is a screenshot from the Fast Forward Working Group taken back several years ago, and you can see a lot of the names on the chart are still members of the organization, but we had a number of spaceports join and participate, and I got a chance to meet some of you through that mechanism, so I appreciate that opportunity. Now, Fast Forward is ably managed as by Oscar Garcia as its executive director, and that continues as its own organization as well. Okay, let me talk a little bit about hypersonic flight and what our vision has been, the vision that my company has put out. And that is that flight faster than, let's say faster than Mach 2, has a place in the ecosystem and the economy of a global community. Being able to shorten the distances and times between various points on the globe, whether for passengers or for cargo or both, is an idea whose time is coming. There are obstacles, to be sure, both economic and regulatory. There are a number of technical obstacles to be overcome that are even harder at the flight velocities that I'm talking about here than they are at supersonic. Say Mach 1 or 2, maybe up to Mach 2.5. The problems that we produce at higher Mach numbers are more difficult. But this is a vision vehicle that my company put out in partnership with our work for Fast Forward called SaberCat. And it represents a 20-passenger elite airline, or honestly, private owners are able to afford aircraft like this in limited quantities, or charter or fractional ownership types of operations could buy aircraft like this. This particular one is capable of traveling at Mach 4.5, 20 passengers, about 7,000 nautical miles. And let me give you a sense for how big that is, because that's something I think as spaceport operators, you all need to have a handle of what we're talking about here. Aircraft that have high flight speeds and long range tend to be very large, at least relative to what you might find in a subsonic or a transonic business jet. These aircraft are very large. So SaberCat here is over 500,000 pounds of takeoff gross weight. I said 20 passengers. In fact, it's 16 passengers and then plus crew. So 16 passengers on board. 200 feet long, and that compares to different high-speed or different supersonic aircraft that you might be more familiar with on the left, including the SR-71, the Concorde, to which we're all compared regularly, and then the XB-70 are all shown on this chart. So the SaberCat, being a 16-paying passenger aircraft, is rather large. And this particular baseline, we've assumed a turbo ramjet. So again, that's a combined cycle propulsion system that combines a turbo machinery, classic type of turbojet, with a bypass system that would enable it to travel faster using a ramjet mode of propulsion. Propellants here are a combination of Jet A, so traditional hydrocarbons, and liquefied natural gas. So the ramjet flies on liquefied natural gas. No onboard oxidizer, so there's no rocket mode associated with this aircraft. So over the last 15 years or so, our company has built up a position. Our company has built up a position of things that we think are the most attractive areas for high-speed point-to-point, PTP, point-to-point travel across the Earth. So some basic questions that are out in the industry today are, as I mentioned earlier, should we have cruising vehicles or should we have ballistic vehicles? I think we've all seen the SpaceX video that was put out a couple of years ago in advance of the IC meeting in Australia that showed a vertical takeoff rocket launching from New York City Harbor and landing in Tokyo, and large number of passengers. And of course, that's what Starship is based on today. And that is opposed to an aircraft-like operation. Our company position is that aircraft operations have a number of operational advantages that cater to the traveling public. We all are familiar with getting on an airplane. We're all familiar with accelerating down a runway and taking off and having abort or recovery modes that return us to that airport. Shirt sleeve environment, low acceleration environments, relatively low heating environments. So our company tends to favor the cruise type of operations. Rockets versus air breathers, we typically favor, as I mentioned a couple of times, a combined cycle propulsion. Here, I think turbo ramjets. I do have the additional comment on this slide that suggests that I think green, so-called green propellants or synthetic propellants are likely to emerge as being particularly compatible with this operation. If for no other reason, they tend to mitigate a little bit of shaming or pushback that would happen to people that can afford to travel at these speeds in terms of emissions. And so having green propellants might help mitigate some of that concern from an emissions point of view. I can talk about emissions if someone would like. Aircraft range, here I mean unrefueled range, 4,000 to 7,000 nautical miles, and I'll spend a lot more time talking about that. Speed, I'll spend some time talking about this, but our company position is Mach 3 or 4, let's say 2 times what most investment is being made today as the cutting edge, and move that forward to Mach 3 to 4. Sonic boom remains a major concern for supersonic flight. I can address that if you like in more detail, but over ocean routes are plentiful, and we think they should be the basis, or at least the initial basis for operations, particularly trans-Pacific routes. And then on the issue of cargo or passengers, the answer of course is both. It's just a matter of when. And so a good development and risk reduction and regulatory risk reduction activity could be to start with cargo and then advance to small hypersonic business jets or high-speed business jets, and then finally larger transportation class. So that's the development path that we see as an organization. All right. With that, if there are no questions now, I do want to address the main part of the presentation, which is what exactly did we do under sponsorship to NASA, and what did we find? And I'll spend about the next 10 or 15 minutes speaking about those results. I will say that the results are being made public. So NASA plans to release both studies as soon as possible. I know our team has just put in the final edited and revised version of the final report with NASA approval. And so NASA intends to publish those. So what I'm going to show you, it will eventually be public information, both in a written report format as well as a PowerPoint style presentation format. The final PowerPoint presentations have already been delivered, and those presentations have been made. And I suspect that NASA will distribute those on a public website as well within the next month. So that's the status. The genesis of this is we got together with the Hypersonic Technology Program Management. Chuck Leonard is a name that comes to mind out of NASA Langley Research Center as one of the leaders of that organization. And Jimmy Kenyon out of NASA headquarters and ARMD is another leader of this overall effort. And they asked the community, what is it do you need from NASA, and how can NASA or the government help you in the work to advance US interest in high speed or even hypersonic flight specifically? And one of the items was we need market research. We need independent market research and analysis, because frankly, one of the things we struggle with in this community is a bit of doubt that comes primarily from the economic failure of Concorde. People will ask, if Concorde was not successful, no one else adopted widespread supersonic flight capability, what has changed? You know, what's different? Is the market any different? Can this be economically supported? And I think we all anecdotally think that if you're on a long flight, say from the Western United States to Sydney, you might at some point say, my gosh, I would pay a little bit more if this aircraft could go faster. That's a 16 or more hour flight, and when you're on it, it seems like, you know, hey, I could pay 20% more to go faster. So we have in mind that there's a premium to be paid for speed. We all know that sort of intuitively, but how much? Is it 50% more for 50% more speed? Is it 10% more for 100% more speed? What does that price elasticity look like? And honestly, there are companies in our community that do this kind of independent assessment, market assessment, and companies, and we're fortunate to be one of those, that can then turn it into economic numbers. And so that's the genesis of this. NASA put both teams under contract about in August of last year, and we did our final conclusions in February. And as I said, we're just now polishing off the final reports for them to be made public. And I'll give you a little bit of a preview of the one that I was fortunate enough to work with. Okay, it starts a little bit with points of departure. NASA gave us a design box to consider of between Mach 2 and Mach 7, between about 3,000 nautical miles of unrefueled range and up to about 8,000 nautical miles of unrefueled range. And then the numbers of passengers was anywhere from about 20, 15 or 20, up to about 250. So it's a big design space. And the answer is, are there parts of this design space that make economic sense? There are a number of players, I'll show you that on the next chart, who are at different parts of the design space. Does any space here make sense? And then the follow-on question is, if the answer to that is yes, then what do they look like? You know, what are the groupings? What are the sweet spots, I guess to say, in that space, if there's anything that does make sense? So our points of departure were these historical reference vehicles that we calibrated our economic and our sizing models to as we bounded this trade space. And Concorde we're familiar with. The TU-144, the Concorde Ski, is one that you're probably also familiar with. If you've been in the industry a long time, in the lower left and the lower middle, you're familiar with some of the US-led supersonic transport, SST, designs that were created but never fielded in the 70s, early 70s. Top right, high-speed civil transport was a NASA study to look at high-speed, although not hypersonic, transportation as a civil investment that could be made. And then we're familiar on the military side with the SR-71. So this is a sample. There are a few more that we considered as well, but this is a sample of the aircraft that we use to calibrate our models. And then looking forward, there are a number of private entities that are raising money, getting down payments, receiving orders on future aircraft that are high speed at least, supersonic, maybe even some hypersonic flight vehicles that are being invested in, and that work is underway. You're probably following all of these, but I will point out specifically that Ariane came out with an announcement here in the last week on the AS-3, which I'm not showing in this picture, but that's announced to be a Mach 4 aircraft capable of traveling 7,000 nautical miles unrefueled. So a longer range and a higher flight velocity configuration coming out of Ariane. Boom, making great progress on their vehicle, and including some test demonstrators. Spike in the middle and the top, you're probably less familiar with, but they also are operating in that space. Virgin Galactic, and I show a notional picture here. Virgin itself has been a little bit, played their investment close to the vest, but they're looking at Mach 3 with some synthetic fuels. We had a briefing on the fast forward side from Virgin recently. And so the configuration is a bit notional, but they're operating in the Mach 3 space. Hypermach and Hermeus. Hermeus is a local Atlanta-based company. Here are looking at higher speeds, higher parts of the flight speed range, including Hermeus here at Mach 5. So this is the up and coming, and we use this data set also to calibrate some of our economic analyses. Alrighty, so I told you a little bit about the trade space. Let me start with something basic, which is takeoff, acceleration, cruise, descent, approach and landing, and taxi model. So one thing when you're looking at high-speed transportation and talking about the maximum cruise velocity of a particular aircraft configuration, they don't always fly at that speed. And so you have a big investment in near airport operations or near spaceport operations, takeoff, acceleration. And so you can imagine, I guess, a thought process that says, if the aircraft could travel at Mach 25, would it? And the answer is no. Our Earth basically is not big enough to get to a cruise condition like that with any reasonable acceleration on the passengers. So as a function of distance, speed does play a role. Longer distance speed, you can actually get to that cruise condition and maintain it for a sufficient amount of time. So we created a parametric model that could look at that for a variety of ranges and a variety of travel times. And so this chart is a bit much to take in, but let me just point you to, on the horizontal axis on the x-axis is the design range of the aircraft. On the vertical axis is the gate-to-gate travel time measured in hours. And the speeds that I've plotted here on the top line are subsonic. Let's call that Mach 0.85. And then as I can travel faster, I realize gate-to-gate time savings, but it's not linear. You can see that the lines begin to stack on each other fairly closely when I get to Mach 4, 5, or 6, such that the marginal advantage of traveling Mach 5 in terms of real time, because of the takeoff and landing and acceleration, deceleration phases of the mission, begins to be a diminishing proposition. So how fast is fast enough? It's gray. It's a gray area. It depends on how far you're traveling. You can see out to the right where I'm going from Los Angeles to Singapore. I still realize some measurable, 30 minutes an hour savings for traveling faster. But if I'm traveling from New York to London across the North Atlantic, there's a diminishing return beyond, well, you might say beyond Mach 3 for sure, maybe somewhere between Mach 2 and Mach 3 makes a lot of sense for that. It is more complicated than this, and the idea of a one-day business traveler turn between New York and London and back in the same day, for example, is particularly attractive beyond just travel time. It enables a one-day business meeting. Similarly, travelers coming from Tokyo to Los Angeles and back again can make a one-day turn coming across the Pacific if you travel fast enough. This is a rather simplistic way to look at it just in terms of time, but based on this, we would argue that the Earth is just not quite big enough to realize substantial savings between Mach 5 and 6 or 4 and 5, and that a sweet spot might pull you back below Mach 5. My company spent a lot of time looking at economics, and we have a reasonably sophisticated economics model that allows us to consider the manufacturers as well as the operators and owner-operators of aircraft, and who will pay what amount for which one, and how can they all be healthy at the same time? How can the engine providers make money? How can the airframers make money? And how can the various operators, either commercial or fractional charter, make money? What I'm showing you here are the routes that our team, that is the Deloitte NIA Spaceworks team, considered in our modeling for scheduled passenger service. So only one element of the market, the scheduled passenger airlines, and the markets that we considered. So we considered and characterized 90 different routes over the course of the study, characterized them with ticket price versus passenger elasticity. So each of these markets and ranges were characterized by how many passengers typically travel the market, how much are they willing to pay, and how much are they willing to pay for more speed. So all mathematically characterized. You can see some of our biases here that we introduced. For example, one of the most lucrative and busiest routes that we're familiar with is the East Coast of the United States to the West Coast of the United States, the New York to Los Angeles route. That is not a route that our team modeled. It's not a route that we modeled. We did not model some of the intra-Asia routes that are also very profitable for their operators, but they don't make a lot of sense for high-speed flight. And because they're short, in the case of the transcontinental flight over the United States, it's difficult because of sonic boom issues, and we chose to avoid that. So we said, if this is the market size, these 90 routes, is that sufficient to generate within this big box that NASA gave us? Is there anything in there that makes sense economically? Okay, so you can see a lot of interesting routes here. Certainly not an exhaustive list of routes that could be serviced by a high-speed system. It's just what we chose to model as sort of a minimum viable set. Okay, what you would care about is not only those lines. Okay, I showed you that I can connect New York City to London, but also showed you I could connect Charlotte, North Carolina to Lagos, maybe, for example. You know, those are not all equal routes. And so if you take a chart like this, where there are two axes, the horizontal axis is still unrefueled range, but how much is fast enough? And I identify in the little bang box at the top that if you take 5,000 nautical miles, if you can find that on the screen, I don't know if my mouse works or not, you find that one and you go up and you find that there are almost 73% of the available traveling public could be addressed by an aircraft that had a 5,000 nautical mile range. If you look at, say, some of the 4,000 mile range and consider only the trans-Pacific routes, you would get 50%, looking over here to the right, you get 50% of the potential market available in these 90 routes just with a 4,000 nautical mile airplane. That is because the North Atlantic routes are dominant. The travelers across the North Atlantic from the Northeast United States to Western Europe are currently some of the largest and most heavily traveled transoceanic routes in the world. And so you don't really have to go out here to an 8,000 nautical mile aircraft, 8,000 nautical mile range aircraft, at which point, yes, you would get every route and every passenger on that route would be available to you. But it's a diminishing return. You know, you can get 5,000 miles, you get 73%. You can see how that curve behaves. So we do consider that explicitly in our model. If an aircraft is capable of capturing more markets, it tries to, but it's not always the best economic thing to do. I do have a chart here that addresses the price elasticity. I won't belabor it too much, but if you're familiar with me and the work that I've done in this area in the past, we've used a simplified model here, derived from some work we did with Derek Weber at Spaceport Associates, which are the two blue lines. This is a particular route out of the 90. This particular one is JFK to London Heathrow. And you can see how the new data gathered and researched extensively by Deloitte behaves much differently than what my company used to use. So we consider the orange lines to be now more accurate and up to date. And again, we have it for all 90 routes. And that is the data we used to do our work, is the orange lines. You can see the things that we like to talk about here in high speed, where the orange line here is Mach 2, say, at a given price point. The Mach 5 point, which is in lighter orange or yellow almost, would produce more passengers. That's the intuitive feeling that we have, that people on an airplane are willing to pay a little more to travel faster. And so you can see you could get more passengers that could pay a little bit more. That's how it behaves. But that's how all these price elasticity curves look as a result of the research, and they will be documented in the final report. Some key assumptions, I won't belabor this, but I do need to put them in. We modeled a single aircraft traveling along its design range, but it can travel shorter ranges than its design range, of course, by offloading fuel. We modeled 2021 to 2055. 2021 is not the earliest entry into service. It's just when you start expending money. That money is usually the engine developer who goes first. We do make an assumption that the United States government does purchase an anchor buy in our modeling. We use turbo jets and turbo ramjets in item number 4. And then in order to be captured in the analysis, you have to be one of the 90 routes and have the sufficient range on the aircraft. All right. So I realize I'm running a little short on time. George, could you give me some feedback here, or Steve?
I'll try to finish the next 5 minutes if you can. Next 5 minutes if you can.
5 minutes?
Yeah. Yeah, John, George, I did speak with Steve. We can run over a minute or two. So
Okay.
do the best you can, John.
Okay, I've got about 10 more. I'll try to accelerate a little bit, but this one is representative of the kind of results that you'll see in the full report when you're able to download that. IRR is internal rate of return. Think about that as the rate of return that gets paid back to the various manufacturers and operators. And on this chart, these pickup stick looking charts, the objective is to have a higher IRR. So being higher on the vertical axis is preferred. The royal blue line represents the trade space of different design ranges for the Mach 2 aircraft. This is for 50 passengers only. And then going down on the lines and the colors, you can follow along to the different higher speed aircraft. So if you're a proponent of a Mach 2 to 3 aircraft, you can see that on average, your rate of return in the models as we did them is better and best, even in the case of Mach 2, discretely considered Mach 2, than the competitors most of the time. However, for the shorter range routes, that is the 3 to 4,000, you can see that the Mach 5, or just barely under Mach 5 is what that is, did actually produce a higher IRR than its competitors, although the best IRRs typically were in the 5,000 plus or minus range at Mach 2. So we consider that to be a interesting result in that speed doesn't always win. Faster speed produces more expensive aircraft, produces larger aircraft, and so that turns out to be an economic disincentive at some point. And slower aircraft tend to be more affordable and more affordable to a larger segment of the public who would maybe want to buy one. I won't spend a lot of time on this chart. You can see them if you download the full report package from us, from NASA. One of the things you see is that the Mach 2 aircraft on the top chart here sells more airplanes. They're more affordable. They resonate better with the charter and fractional ownership market, and there are even some high net worth individuals that can afford a Mach 2 aircraft. And so number of aircraft sold is good for the manufacturer, and that lowers the average price of the airframe. So that's an advantage for a little bit slower airplane. Number of passengers that we pick up per year is greater. That's because the ticket prices are less, and you can see the effect of ticket prices. Just one basic takeaway is that early in some of this high-speed point-to-point travel, we would talk about ticket prices in the in the $10,000 to $20,000 range. I even heard some people say that they would be in the $100,000 range for a ticket on an aircraft that could travel halfway around the world or a quarter of the way around the world. Our models do not support that. Our models say, if you look at where Concorde would be, maybe $3,000 per direction, about the same. Across, there are charts available like this in the final report too that are more extensive that show you the sweep of Mach number and passenger count versus range. I've circled some interesting points for you on the top left where the internal rate of return is high, above or near or above 30% for all players in the economy relative to other places you can be in the market. But honestly, 20%, 25% might be attractive to some folks. So of those people that are venturing and making investments in this market, I don't fault any of them. Nobody is wrong. There are different parts of the trade space, depending on speed or range, that maybe make sense to them for them to compete in. And if you say, hey, I'm satisfied with 20 or 25% return, that's great. Then you'll find an area that works for you. Our position, however, and I'm going to skip to some conclusions here in the interest of time. Our conclusions are that the Mach 2 to 3 cases seem to be the most robust. So basic NASA question here, number one, does anything make sense above Mach 2? The answer to us is yes. There are cases that produce attractive IRRs anywhere from 2 to slightly under 5. 2 to 3 just seems robust to us from a passenger count and a production. It's kind of a nice place to be. Question 2, what aircraft sizes make the most sense? Are we talking about transport class aircraft, or are we talking about bizjet class aircraft or something else? And really the smaller ones made a lot of sense. They have higher utilization rates. That is, they travel at a higher passenger load factor and make more flights per day. And they also have a lot of synergies with different segments of the buying market. That is the corporate jet and the private owner jet. So we like the smaller jets. I addressed ticket prices already. They're definitely not $100,000 to make money here. They're more like, you know, Concorde type prices per direction. What about range? And I emphasized that the transatlantic routes are plumb, but we believe that the trans-Pacific routes are emerging. Economically, a 4,000, maybe 4,500 nautical mile range is a good place to be. Stretching out to trans-Pacific is more expensive. It requires more capital, a bigger and more expensive jet, but there are emerging markets there that can and should be addressed. How much do the aircraft cost? I mean, if you were to buy one, let's say by comparison, Gulfstream G6 is, let's say 75 million, give or take, depending on how many gold toilets you want inside it. But these aircraft will be about twice that. Not absurd, but definitely more expensive. What are the gotchas? The market elasticity is huge. The market elasticity curves that say people will pay this price is huge. If you compare on the cargo side, the number of people who have same-day shipping, say from a shipper like FedEx or UPS, it's very, very small compared to the people that take two-day shipping. So that elasticity is sharp, but we have a lot of confidence in the analysis that our team did to try to characterize those markets. All right, I apologize for taking so much of your time and for kind of the awkward start here. But with the time left, I'll turn back to the group to see if there are any questions. If I've used up all of your time today, then I thank you for your attention.
Oh, that's excellent. Thank you, John. And for anyone who does have a other commitment and need to drop off, that's fine. Feel free to do that. But we would like to stay around for a few minutes if possible for some questions. And let me just start off by asking you, John, what are your thoughts on how the spaceport community can play a role here, even though that in your study you essentially did not look at the East Coast, the West Coast of the U.S. Once we start building these things and flying them, there's going to be some testing requirements and so forth. And so you alluded to all the regulatory requirements and the sonic booms and other things like that. Is there a role for specifically spaceports or other specialized airports in development, testing, demonstration of these kinds of vehicles? It looks like you're muted.
Yes, thank you, George. And I think the answer is yes. And so I have been an advocate for utilizing the spaceports both individually and in networks, partnerships and networks to help with testing and flight demonstration. I mentioned too before that my own company had partnered with Cecil in Jacksonville to do overwater testing of an expendable system that was a research platform, fly out of Cecil, but then splash into the Atlantic Ocean. I, in the past, have explored options to partner with Jacksonville, Florida, and Glasgow, Scotland, as a great natural link. I know that we've looked collectively as a group at Midland to Spaceport America. We've looked at the triangle of Front Range, Spaceport America, and Oklahoma as being potential interesting ranges. Let me give you some thoughts. For a expendable vehicle testing up to Mach 5 for about a minute or so, we needed a range of about 160 miles, 160 nautical miles. So it's a big requirement. At Mach 5, you're traveling a mile per second, and that's at cruise. So you still have the part to get up and the part to get down, and you're traveling a mile per second. And so the ability to test really high-speed systems at a single spaceport is limited, unless you have a unique system where you could fly out and on a subsonic airplane and fly back hypersonically, but about 160 miles. Now, for something that's more reusable, I think we're looking at ranges that are significantly longer than that for testing, maybe as much as 1,000 miles. And one of the constraints becomes turning. An aircraft traveling at Mach 4 or Mach 5 has a very large turn radius to stay underneath about, let's say 1.5 Gs. You want to give me 1.5 Gs? It's a big turn radius. And so the corridor, the test corridor, we need to think about it either as being a straight line distance that could be as much as 1,000 miles between nodes, or a way I could fly out of a corridor over the ocean, do a turn, a very large turn, and then fly back into a corridor. When NASA and the Air Force tested some of their high-speed systems, they tested over a Pacific water range out of Edwards and then up and down the West Coast. So that's of interest. Over land, I think we have to look at places that are, let's say, are far enough apart. In terms of the corridor, I didn't show you, although I do have the charts having to do with sonic boom. If I'm high enough, I could show you a chart looks like this. If I'm high enough in altitude, and the faster ones, faster aircraft tend to travel at a higher speed. My sonic booms, which will be the purple lines on this chart, tend to be about 1 pound per square foot on the ground, measured on the ground, where 1 to 2 is problematic for people. So in terms of sonic boom, I think you have to have a corridor that's tolerant of that has sparse population density underneath the corridor. I know I've seen the one proposed out of the Global Spaceport Alliance over Kansas, in and around Wichita, or on either sides of Wichita. That I think it is a little short, but I think otherwise it's well positioned. The one from West Texas to Spaceport America is interesting because of sparse population densities. Some others might run into some more challenges there, having to do with it's a more metropolitan cities or major cities that could be close to those sites. So I would worry about overflight over land.
Couple of quick questions, if I could try to get in. Got one asking, did you take into account environmental or CO2 emissions as part of the study in any way?
Yes, and this is representative of that. So it wasn't a constraint, George, or whoever asked the question. It wasn't a constraint, but it was something that we calculated parametrically for every aircraft that we designed. And we designed hundreds of point aircraft within this box, and we considered it as a metric of output. And you can see in this chart that I have from the final report, some of the notional aircraft in the first 4 columns compared to existing or historical aircraft in the columns to the right. So one of the things people care about is carbon dioxide emissions, CO2, or CO2 equivalent, what we call CO2e, a little e at the bottom. That's equivalent greenhouse gas, whereas CO2 is a greenhouse gas by itself. And you can see the amount of particulate matter or emissions produced by these aircraft on either a kilogram per kilometer, that is, how much per distance, or per passenger, which is how ICOA measures it. They have something called metric value, which is essentially a kind of like a per passenger calculation. And you can see that the little aircraft on a per passenger basis are high on this metric. I'm showing you a 4 here. So it was considered, it wasn't a constraint.
Okay, and one final question then. How about ground support equipment compared to a traditional aircraft? Anything special that would be required for a vehicle like a Sabercat?
Yeah. Yes. And one of the things on Sabercat in particular, I did point out that it uses liquefied natural gas to provide the fuel for its ramjets. So I think as an operator of a spaceport, you would have to have unique propellants. We did try to stick to Jet A to the extent we can, but there's some unique hydrocarbons as well, but then liquefied natural gas. The aircraft are hot. They get thermally hot on the outside, and they have special materials and material handling on the skin on the outside that could require some unique ground support equipment having to do with inspecting and maintaining exterior skins. But I think the fuel requirement may be the biggest one.
Okay, excellent. So I know we could keep going for quite a while with all the questions that you've generated here, but excellent presentation. I hope we can reach out to you later if we have some follow-ups, especially after the reports go public from NASA. But
Of course.
Excellent conversation. We certainly would like to partner with you and others on how we can make this happen in the near future. So with that, I think I'll turn it back over to James for final thoughts.
Okay, John, that was absolutely amazing, as George said. Thank you very much. And frankly, at this point, I think that we've gone over quite a long time, so I'm going to have to defer, Oscar, your update on the working group until our next meeting. Okay.
Thank you very much. Nothing else to say after John's presentation. Superb.
Okay. Okay. Well, stay tuned. We've got a lot happening with GSA, and looking forward to talking with you all within a month or so. Take care. Okay. Bye-bye.
Thank you all.